So these are the learning objectives of this course. We have already learned assembly programming. Now we will jump into hardware and take a look at CPU I/O communication. So there is a variety of input-output devices available, and this slide shows the diversity. These devices differ from each other in different ways. For example, some devices are only input devices, such as keyboard and mouse. Some devices behave only as output devices, for example, printers and graphics. Whereas there are other devices that can behave both as an input and output device. An example is your network card. The devices also differ in who they communicate with. There are devices that communicate with humans, for example, keyboard and graphics, whereas there are other devices that communicate with other machines. Examples include magnetic disks and networks. Finally, the devices differ from each other in how much data rate they can support. Keyboard and mouse in this aspect are very slow. They support very low data rate, whereas magnetic disk and LAN, especially the LAN, they are very fast. For example, networks can support up to maybe 100 gigabits per second these days, maybe more. Okay, so this slide shows us that input-output devices are very diverse. So we need to support this diversity while connecting an I/O device with the processor. So how do we do that? So instead of connecting the CPU and I/O device directly through a bus, we connect them via what is known as an I/O controller. It has a data register and a status register. The data register holds the data that CPU will read from the I/O device for input devices, and for output devices it holds the data that will be written to the device by the CPU. The status register holds what's the status of the I/O operation or the read-write operation. Has the operation already been finished, or is it still waiting because I/O device cannot support such a high bit rate which CPU can support? So due to the diversity of I/O devices, there are different I/O controllers and different interfaces to connect a device to the CPU. For example, modem is connected using an RS-32 serial interface, whereas other devices use separate interfaces. Printer can use USB, monitor can use a specialized video interface, and so on. And also, since devices behave differently, there are different I/O controllers for different devices. So what you see here is due to the diversity in devices, we have different I/O interfaces and I/O controllers for different devices. Okay, so now how do we know how to address the I/O device? For example, for the memory, it was straightforward. Each memory location has an address and we use load store instruction to access that memory location. But how do we address the I/O devices? There are two ways of doing that: memory mapped I/O and isolated I/O. In memory mapped I/O, we set aside a piece of memory for I/O devices. What does that mean? So let's assume that we have 1 megabyte of memory. So instead of putting physical memory at whole 1 megabyte of memory space, we set aside some of this space for I/O devices. That means at that particular space, what you have is the registers that belong to I/O controller, not the memory. The advantage of such scheme is that you can use regular load store instructions to communicate with I/O devices. So you just give it the address of a device instead of giving it address of the memory, and what you are doing is you are interacting with the I/O device. However, the downside is that I/O devices eats up some of the memory space, giving us lesser effective memory. For example, in our case of 1 megabyte of memory, some of the space is allocated to devices, so we cannot have memory at that space. So the effective memory that we are left with is less than 1 megabyte. The second scheme is called isolated I/O space. It also has other names, for example, I/O mapped I/O or port mapped I/O. The difference is that instead of eating up some space for memory, we have I/O devices in a completely separate memory space. What it means is at the same address, you can have a memory location and an I/O device. For example, the address 100 can have a memory location associated with it and also an IO device associated with it. So if we can have two things at the same address, how do we know with which one we want to communicate? The solution is that we have separate instructions for accessing memory and IO device. For example, in Intel x86, in and out instructions communicate with IO devices, whereas load store instructions communicate with the memory locations. And a processor can support both memory mapped IO and isolated IO. Now let's take an example of memory mapped IO and see how it can be used to communicate with a device. So let's say the base address of the device is 1000. So we saw there are two registers, data register and control register. In fact, there can be many more. So in this case, we have two registers. The first one is located at a distance of 0 from the base, and second one at a distance of 4. So this is the base address of the device, and these are the offset of the registers from the base address. Okay, so now let's do it. So the first thing we need to do is to know where that device is in the memory space. And we use exactly the same way that we did in our assembly programming in the last lecture. So we use an LDR instruction to load the base address of the device into a CPU register. So now we know this is the address from which the IO device registers start. Then to load something from the register 1, we do what we already know. So we use LDR instruction this time. We say R1 has the base address of the device. This is displacement, how far we want to go from the base address. And from this to complete address, load a value into register R0. So this effectively is reading from register 1 of the device. Then if we want to write something to the device, we will first move what we want to write to a register. For example, in this case, we want to write value 8. We move it to the register R0, and then we do a store. So in this case, what we are doing is we are storing the value in R0 to a register R2. So you first go to the base address and tell how far R2 is from the base address, and then the store instruction will place the content of R0 to that particular address.